Let's look at the exact moment the United States officially made the switch from black and white to color television. The broadcast date reveals a technical anomaly. The underlying technology to transmit a live color image had been successfully demonstrated in the late 1920s. This chart tracks the market adoption of television over time. You can see the initial 1928 demonstration marker here, but color households don't actually overtake black and white households until the early 1970s. That leaves a massive 40-year gap between the proof of concept and mass market reality. This delay was not due to a lack of understanding about color theory. Engineers already knew how to separate and recombine light. The problem was that early television architecture collided with strict physical and infrastructure limits. To make mass market color broadcasting possible, 3 distinct engineering bottlenecks had to be solved: the capture limit, the display limit, and the transmission limit. The foundational problem lay in physical mass. Early image systems relied on heavy moving parts that had hit an absolute physical ceiling, requiring a total rebuild of how images were processed. Achieving color television required multi-generational, rigorous systems engineering to circumvent the laws of physics and the constraints of government regulation. In 1925, Scottish inventor John Logie Baird developed the first mechanical television. His apparatus captured images by placing a large spinning metal disc directly between the subject and the camera sensor. This disc had 30 spiraled holes. As it spins, each hole scans a sequential line, allowing light to strike a thallium photoelectric cell. This cell measures brightness changes, converting those photons directly into an electrical signal. Baird eventually added color by splitting the holes on his disc into 3 groups, adding red, green, and blue filters to each section so it would scan the frame one color at a time. But this design hit a wall. To produce a smooth, high-resolution color image, that heavy wheel must spin at unachievable RPMs before flying apart. Bypassing this capture limit meant abandoning mechanical movement entirely and transitioning to solid-state systems with 0 moving parts. The solution arrived when inventor Vladimir Zworykin developed the iconoscope, essentially the world's first video camera to rely on a cathode ray tube. Inside the iconoscope, a lens focused incoming light onto a thin mica sheet. The back was silver, while the front was covered in tiny photosensitive grains. As light hit these grains, they emitted electrons and lost their charge, effectively saving an inverted electrostatic snapshot of the image on the sheet. An internal electron gun then scanned that sheet line by line. When the beam hit charged areas, it bounced into a detector, outputting a continuous electrical wave. By swapping heavy-moving metal for the subatomic manipulation of electrons, engineers broke the capture limit, achieving the high-speed processing required for a detailed broadcast. Capture was solved, but displaying color created a new problem. Early designs, like RCA's camera, used special prisms to split incoming light into 3 separate red, green, and blue feeds. This meant the receiver at home required 3 separate cathode ray tubes, 1 for each color, and a complex series of lenses to recombine those images onto a single screen. Aligning these projections perfectly was incredibly difficult. Even minor shifts created unwatchable, blurry pictures. Worse, using 3 separate tubes made the television 3 times more expensive to produce. For mass market adoption, the industry needed a single-tube solution that was robust and cheap enough to manufacture on an assembly line. RCA engineers developed a new screen coated with microscopic phosphors arranged in alternating triangles of red, green, and blue. At the back of this single tube, 3 closely clustered electron guns fired together, scanning the screen in unison. But the electron beams were simply not focused enough to selectively strike only their designated subpixel color without bleeding into the adjacent phosphorus. The fix was an exercise in pure geometry. Engineers placed a metal plate with thousands of tiny holes behind the screen, called a shadow mask. Because the 3 electron gowns are spaced slightly apart, their beams approach the mask at different angles. They cross paths inside the hole and diverge on the other side. The metal physically blocks the errant particles, ensuring the blue beam can only ever hit the blue phosphor, and so on. Using a simple, physical piece of perforated metal to geometrically block subatomic particles solved the display bottleneck, driving manufacturing costs down to a consumer level. By the time color was ready, There were already over 5 million households in the United States using these standard black and white televisions. This chart visualizes the radio frequency spectrum. The FCC mandated that a television channel fit exactly into a 6 MHz bandwidth block to prevent interference with military and aviation signals. A standard single-channel black and white signal fit neatly inside this 6 MHz limit. Broadcasting 3 separate red, green, and blue color signals would require 3 times the allocated bandwidth. This would violate federal law and render millions of existing televisions instantly obsolete. The workaround required complex signal multiplexing. Engineers mathematically separated the video data into an overall brightness signal, called luma, and the raw color data, chrominance. The luma signal is essentially identical to a black and white broadcast. It can be transmitted normally, allowing all older televisions to display a perfect monochrome picture without hardware upgrades. The remaining color data is mapped using specific mathematical formulas to create 2 distinct signals, I covering orange and blue hues, and Q covering green and purple hues. To transmit them together, these I and Q signals are converted into sine waves and phased exactly 90 degrees apart. This combined color wave is modulated at a specific frequency of 3.57 MHz. This allows the color data to hide in the microscopic gaps of the luma wave, squeezing all that extra data into the 6 MHz limit. When this dense signal reaches a color television, it detects a short burst of a 3.57 MHz reference wave at the start of each scan line. By comparing the incoming wave against that reference burst, the television measures the phase difference. It untangles the I and Q signals, reverses the formulas, and sends independent voltage data to the red, green, and blue electron guns. Compressing 3-dimensional color space into a single backward-compatible wave was an elegant solution to a harsh infrastructure constraint. When you combine these 3 independent solutions, you get the actual physical pipeline of analog television. First, incoming photons strike the photosensitive grains inside the iconoscope, converting light mapping directly into electrical charge. That charge data is calculated into luma and chrominance, mathematically phased, and hidden within the strict confines of a 6 MHz radio broadcast. Finally, the television decodes that wave and fires 3 synchronized electron beams through the shadow mask, relying on physical geometry to perfectly illuminate the phosphor triad. This complex, precise sequence executes line by line, generating a seamless, high-resolution color frame in a fraction of a second. This functional pipeline required a precise synchronization of solid-state physics, optical geometry, and advanced signal processing. This specific, rigorous architecture became the NTSC broadcast standard in the United States, and these specific engineering workarounds were so effective that they defined global television transmission for over 60 years, only ending when analog finally gave way to digital. The greatest technological achievements rarely stem from limitless possibility. They are built by elegantly folding massive new capabilities into the strict, unforgiving constraints of the physical and economic world.